Here we are. This is the Chapter 7 test review. You can see on the top it says 7C. So this is version C, which is a little bit harder than version A and B. So it should over-prepare you for this test. Let's dive in. Number one is essentially getting at um, what the difference between a parameter and a statistic is. So you've got here it says 19% of all cars. So that is talking about the population. So it is a parameter. And then here it says there was a sample, and samples produce statistics. And 22% of the cars in that sample were white. So that is B. Um, Pretty straightforward. Number two, the best test statistic for estimated and parameter. It's going to have low bias. You never want high bias, which that one's pretty obvious. So low bias is better than high bias. And then you've got high variability for these three. You don't want that. You want the spread or the variability to be low. Um, so then the data is tighter to the mean, right? If you have your curve and if you have high variability, it's kind of a low gradual curve like this, and you're trying to, there's your data centered in the middle. But if you can tighten the data, it would be a little bit like this. And so more of your results are going to be closer to the center, which is good. So low variability is better. Number three, which of the following best describes a sampling distribution? So this is the definition of a sampling distribution. Um, A and C are close, but this is why they're wrong. It is a sampling distribution is when you put a dot on the board, and we've been doing this a long time. Like each of you takes your own sample, gets your own statistic from that sample, and then puts your dot on the board. Technically, to be a sampling distribution, it needs to be all the possible samples listed on the dot plot. So large is good, but it's not enough. You need all of them. So technically, we've never done this in class because we have not put a dot on the board for all the possible samples, all the possible values that it could take on. So there would be like hundreds, if not thousands of dots to make it a sampling distribution. It is not D because this is a distribution of the parameter values. Um, it's not, these dots are not parameter values. Remember the parameter value, there's only one of those. There is only one true parameter for the population. So it wouldn't be much of a distribution. It would just be one single dot. So it's not this. And what's wrong with B? It is the set of all values of a variable in a sample of size n. Um, so it's not just the values of the variable, it's you take samples of from the population. So you're taking samples of a lot of values, and then you're averaging them to get X bar, and then that dot of X bar is what goes on the graph. Um, like these could be X bars, they could also be P hats. They are not simply values of the variable. So that's E. Number four. Um, Four describes the population. Okay, the population has a mean of 112. That is mu. Okay, and the standard deviation is 20. So that is sigma. Again, this would be the standard deviation if you sampled one random person, one random adult. Okay, but now we take a sample of 200 adults, so n is 200, and what are we doing with them? We are doing a sampling distribution of what? Of the mean IQ, average IQ. So on your cheat sheets, right, you always have to be deciding, are you here or are you here? And it said sample means, so we are here, okay, this side. And furthermore, it's asking you about this sampling distribution. All the options are more or less saying like wh which option is describing this correctly, okay? It's centered at mu, and the standard deviation is this formula right here, okay? So keep those in mind while I go back. It says the sampling distribution of the sample mean. In other words, this curve, what do we know about it? They're all getting at like, is it normal or not? Where's the mean? And what's the standard deviation? Well, they're all the means are 112, so that doesn't help us. Is it going to be exactly normal? That scares me. No distribution is ever perfectly normal. So never ever pick the ones that say exactly. It's always approximately normal. So you're down to B, C, or D. Then standard deviation will decide it for us. So which one of these three is it? Well, this is the formula that's on the cheat sheet. And sigma is 20 and n is 200, which leads you to C, 1.414. So this sampling distribution, if you all took samples and came up to the board, we'd have a lot of dots right at 112 because that's what we expect. You'd have some dots a little bit higher, right? Some dots a little bit lower, a couple dots way down here, right? But it would be roughly normal, and the average would be centered here with a standard deviation of 1.414. Number 5, studying the effects of acid rain on trees to see um, what percent, here's a percent, what percent showed damage. So immediately on my cheat sheet, I'm like, oh, it said proportion or percent. So everything for this question, you should be looking here on the left column. Okay, and what does it say? It said there was a random sample of 100, so that's N, and 40% of them showed signs of damage. So this is the result of the sample. This is P hat, okay? Which of the following statements is correct? Let's go through the wrong ones first. B, if we took another random sample of trees, we would find 40% of those would show some signs of damage. Uh, no, okay. These are random, right? Every sample is random and you're gonna have different results. Um, given, well, I put here, it is probably the most likely outcome, but it's not guaranteed. You could get higher than 40% or lower than 40%. C, if we did a sample of 1,000 trees, so we're just upping the sample size, the variability of the sampling distribution of the sample proportion would be larger than in the sample of 100 trees. And this is, I crossed off larger because it would be the opposite. If you increase sample size, you are reducing variability. And I'm really focusing on variability or standard deviation here. So let me look at the formula again. Again, I'm over here. Here's your standard deviation formula. Focus in on the n, right? The original sample was 100. Put 100 here, right? Okay, and then it says, what if we increase that to 1,000? If I add a 0 on here, what's going to happen is this number is going to get smaller, not bigger, because I'm dividing by 1,000 rather than dividing by 100. So increasing sample size always reduces your standard deviation or variability. So it is not C. What's wrong with D? The standard deviation of the sampling distribution of the sample proportion of damaged trees is this thing. That's not the formula on your cheat sheet that I just showed you. It's actually the formula for a binomial, which was the last chapter. So they like to do this. They throw something on there that you're like, oh, I'm familiar with that. I've seen that, but it ain't right. It's not going to be E because it is A. The sample distribution of the sample proportion of damaged trees is approximately normal. So looking at your cheat sheet, large counts says if you do N times P, right? That's this top one. And the bottom one is N times 1 minus P. If you do both of those, you should have at least 10 successes and 10 failures. um, the only thing that's a little bit sneakier, trickier, maybe might confuse you is it's P here, but they never told us P here, right? So this is maybe a little bit of a stretch, but if we had the curve, where would this curve be centered? Well, our sample is suggesting the center of the curve is 0.40, and the center of the curve is P. Um, and so I'm going to use I think it's fairly safe to use 0.40 for P. Also, another thing that I feel pretty comfortable about is that both of my successes and failures are far, far bigger than 10. It's not like they're close. 40 is way beyond 10. Even if my sample proportion was incorrect, let's say it was a little bit off. I mean, I can take this all the way down to 10% and I'm still going to have 10 of these. So I feel fairly confident saying that A can be assumed. I'm fairly confident that even though it's a P hat, I can safely use it as P. 6. Which of the following statements is true when you take a random sample? So all three of them are true. Let's talk about each one. The sample distribution of X bar has a standard deviation of this, even if the population is not normally distributed. So this is true. This is on your cheat sheet. Okay. It's true. However, that they're trying to this even if they're trying to scare you or trying to test you. You can always find the standard deviation. Whether or not you use it to find a z-score is is where you want the curve to be normally distributed. If it's approximately normal, then you can find a z-score, and then you can use the empirical rule, the 68, 95, 99 rule, to get the percentages. Okay? Um, so, so if it was not normal, then proceeding to find a z-score would be kind of an inaccurate step, invalid step, okay? But that doesn't mean this doesn't change. 2, the sampling distribution of X bar is normal if the population has a normal distribution. Yes, this will be on the test too. If it states that the population is normal, it's like a get out of jail free card. If the population is normal, then all samples of any size will also be normal and that we're sampling. Okay, so that's true. If the population was skewed, that would be different. If the population was skewed, then you would have to satisfy the CLT, which is next. When n is large, the sampling distribution of X bar is approximately normal, even if the population is not normal. And we've talked about this, right? Even if the population is skewed, in other words, not normal, if it starts out skewed, then for small sample sizes, the sampling distribution would be skewed, but it says large samples, so we're good. This is the CLT. So they're all true. Number 7. Suppose you're sampling from a distribution that's strongly skewed left. Which of the following statements about the sampling distribution of the sample mean is true? Um, this is essentially coming right back to the CLT. And here's what the CLT says again in other words. As n increases, as the sample size grows, the sampling distribution becomes closer and closer to matching the normal distribution. Even true for skewed data. So the one that says that, which one says that? I believe that's just A right there. Okay. Yes, it is. Um, let's look at some of the wrong answers. We can learn from them. As the sample size increases, I'm looking at B, as the sample size increases, the shape of the distribution gets closer and closer to the shape of the population. No, it will get closer to normal, right? If the population is skewed, it does, the sample distribution doesn't get closer and closer to skewed. It always gets closer and closer to normal. C, as the sample size increases, the mean of the sampling distribution gets closer to the population mean. That's not true. The mean is like the center, right? The center remains constant, unchanged. Okay, what changes with sample size is the standard deviation. Standard deviation does decrease as n increases. D, regardless of the sample size, the shape of the sampling distribution is similar to the population. So no, that's saying let's say your population is skewed left, that no matter how big your sample size gets, the sampling distribution will also always be skewed left like the population. And that's not true. The skew will fade away as n increases. E, regardless of sample size, the standard deviation of the sampling distribution is approximately equal to the standard deviation of the population. Um, that's not true. So, for example, this was a sample mean, right? So remember, the standard deviation of x bar is the standard deviation of the population divided by the square root of n. Um, not so. Just think, as they're saying, regardless of sample size. In other words, they're saying n doesn't matter. That they're saying that the standard deviation of this, the sampling distribution, this is from your cheat sheet, is equal to the standard deviation of the population, which is sigma. This is the population standard deviation. And that ain't true. That is just not true. This one never changes. The sampling distribution standard deviation will decrease and decrease and decrease as n gets larger. All right. 8. Suppose we wish to estimate the percent of students who smoke cigarettes at each of several colleges and universities. Luckily, not many people smoke cigarettes anymore. It just isn't cool, man. And we know the damages it does to our lungs. Two of the colleges are Wabash College. I call that WC. And they have 900 kids, very small college. And then there's Purdue University, subscript P. They got 36,000 kids. What should the relative size of our samples be from each school if we want the two sampling distributions to have approximately the same standard deviation? Okay, so we're going to take samples from both schools, and this is what we want. This is the standard deviation of Wabash College and the standard deviation of Purdue. We want them to be equal. It's a percentage. So looking at your cheat sheet, we are on this side. It's a P right here, right? And they're focusing on standard deviation, okay? So that's the formula that I'm looking at right here. And I want this to be the same for both schools, okay? Um, so what we can assume pretty safely, I think, is don't you think P, again, P is the parameter, P would be the same for both schools. The percent of kids that smoke at Wabash College is the same as the percent of kids that smoke at Purdue, okay? Um, so let's keep that in mind. So then if the only thing that might be different is we could take different sample sizes. But if we want these to be equal and P is the same for both, well, then N has to be the same for both. So the answer is D here, okay? We should take the same size from each school, right? They're trying to trick you because this school is so much smaller than this school. That doesn't matter. What matters is the sample size N. If they both have the same sample size, they will have the same standard deviation, okay? Um, so like this larger from Purdue or larger from Wabash is just not true, um, if that makes sense. So maybe put numbers to it. Let's say that P, I don't know, what percent of kids smoke? 15%. I made that up. So for Wabash College, WC, the standard deviation would be 0.20 times 1 minus 0.80 divided by n, okay? But then wouldn't it be the same exact thing for Purdue? Because zero point 0.2 and is the same, or so, where did I come up with 0.2? Hello, Fag. 0.15. Sorry about that. But both schools are operating under the same assumption of 0.15, 15% of their kids that smoke. So they are both, there you go, the same. So if these are going to be equal, n has to be the same for both schools. This is trying to distract you with the 10% rule. 10% rule is for independence. It has nothing to do with the actual value of the standard deviation. Number 9, in order to use here we go again, the standard deviation formula, the sampling of the sampling distribution of a proportion, which of the following must be met? This is just making sure you know what these are. The 10 successes and 10 failures shows normality. That's not what we need. And does the distribution have to be normal? Nope. Okay. And this is actually written on the notes, right? You have to satisfy the 10% rule. And we do that because we have to know that the trials are independent. I even marked this on the cheat sheet right there, right? Check the 10% rule for independence. That allows you to find the standard deviation using these formulas. Okay, and 10. This is a mean or mu, okay? In a large metropolitan area, they found that the time it takes for people to commute to work has an average of 20.5 minutes. That's the population. And a standard deviation of 15.4. So that's sigma. Okay. They're talking globally here about everybody. So that is mu and sigma. What's the probability that a sample, okay, so now they're telling you about that, of 40 people, so there's my n, has an average commute time that is greater than 25 minutes. So they sampled 40 people, added up all their commuting times and divided by 40, and they got an X bar. And they're saying, what's the probability that this curve, you could even sketch it out. The picture always helps me. They're saying for everyone, this is centered at 20.5 minutes. And then you got a sample of, or they're asking you what's the probability of having a commute more than 25 minutes. This is mu, this is X bar. And you're not even doing the work, you're just picking the right formula. So even drawing this picture, I think, should help you because you're gonna get rid of this one because it's subtracting the wrong way, right? It's 20.5 minus 25. So is that one. They're both subtracting the wrong way. You always take the value minus the center. So this would have a positive z-score. So this one and this one and this one all have the correct numerator. Which one has the correct denominator? And this is the formula on your cheat sheet. So that one is sample size of 40. That's this one right here. So the answer is B. Okay, there you go. That is the multiple choice. Moving on. Here, we're talking about beverage companies probably filling their cans of soft drinks like Pepsi or Coca-Cola. The company advertises that the cans contain an average of 12 ounces of soda. Okay, they're claiming that whenever you see the word claim or advertises, right, they're saying this is mu and this is sigma, okay, for all the population. Suppose the company's telling the truth. Okay, can you calculate the probability that a single can has 11.9 ounces? If so, do it. If not, why not? Well, you can't get the probability. I could get a z-score, but when I move one step further and find the probability, I can't do that unless I know the population, unless I know the sampling distribution, I should say, is approximately normal, okay? And it's not 30, it's only one can. So the CLT is not met, so I really shouldn't do this. We can't assume the distribution is normal, so finding a probability based on that doesn't make good sense. So then look what they did on part B. Oh, look, they increased the sample size to 50, thereby meeting the CLT, thereby allowing us to move forward. What are the mean and standard deviation of this? So again, on your cheat sheet, I'm over here because it's a sample mean, okay? Um, the mu, the sample mean will just be whatever the company is claiming. And the standard deviation, we're going to divide by the square root of 50. So they had zero point 0.4. That would be for one single can, but it gets a lot smaller when you have a sample size of 50. Okay, so what I'm doing is I'm setting up my sampling distribution to be centered at 12 and to have a standard deviation of 0.057, okay, which then leads me into part C. They got a sample doing this of 11.9 ounces. That's their X bar for the 50 cans. What's the probability that a random sample of 50 cans has a sample mean of about 11.9 ounces or less? That's why I have drawn my curve and shaded this way to the less than side. Okay, so the probability that the X bar of a sample is less than 11.9 ounces. Okay, and we're going to get about 4%, but you have to find the z-score. So value minus the center, 11.9 minus 12, divided by your standard deviation from part B. Just take your time, be careful. You should get this z-score. And then at that point, you can use your green packets or you can use your calculators. Normal CDF giving me -1, whoops, I should do -99 for my lower, like way down here off the edge would be like -99, way down there. And then the upper is this, like that. So there's my 4%. You could also use your green packets, okay? D, what do you conclude about whether the company is underfilling its cans of soda? Conclude, in other words, interpret this 4%. Is this significant or not? Um, this result would only happen by chance 4% of the time, which is significant. The significant cutoff is 5%, right? So it suggests that there is evidence that the company is not filling it with 12 ounces, rather it's filling it with less than 12 ounces. They're underfilling the cans. 12. Um, this is your proportion question. Okay, there's a sample of 500 adults. There's your percentage, so you know on your cheat sheet, right? It's a P question. Just that should be one of the first things you decide every time. Okay. Um, what did they ask people? Are you in favor of giving parents of school-age children vouchers that can be exchanged for the education at any public or private school? So they ask them if they're in favor of the voucher system. Suppose that in fact 45% of the population favor the idea. So they're telling you P here, the parameter. Okay. What is the mean of the sampling distribution of P hat? So if you took a whole bunch of samples and got a whole bunch of p hats, it would match, on average, the parameter of 45%. If you look further down, it means that your sampling distribution is centered at 45%. Okay. The the sample size might confuse you, like you feel like you have to do something with that 500, but you don't. Um, so there you go. Part B, you do. You take the standard deviation formula, which has the 500 in it. Remember when you do this formula, you use P of 45%, and you get about 2%, 0.022. Okay. C, check that you can use the normal approximation for the distribution of p hat. Going back to my cheat sheet, you're like, huh? Well, that's right here. How do you know the sampling distribution is normal? Large counts, 10 successes, 10 failures. And check it with the numbers they've given you. They gave you 45% p and 500 sample size. This is successes, this is failures. Plenty big. They're both way over 10, so large counts is met. D, probability that more than half of the sample is in favor of the voucher system. That's kind of a subtle way of just telling you that the result of the sample is 50% or greater. So again, it's going to be centered at 45 because that's what I had from up here. What's the probability, though, that you get a sample of 50% or greater? So I have shaded over here to the right side because that would be 50% or greater. So I want to find the probability of getting a p hat. Remember, p hat is your sample result above 50%. So I have to find a z-score for 50%. So that's, that's 50 minus the 45, right? Value minus the center. So this is exactly 5% above average. And then you divide by the standard deviation that you had right here. Okay. And you get 2.27. Hold on, I think my AirPods just died. Oh, maybe not. I think we're still good. Okay. And then here's your z-score, folks. Okay. And you can do normal CDF just like I did last time, except this time the z-score of 2.27 is on the 2.27 is the lower and the 99 is the upper. So that's where I got my percentage right here of 0.0115. So very unlikely. About 1% of the time this will happen. Okay. Last question. Take your time to read this, okay? But it's giving you a lot to read. It's tracking the number of orders filled per day for an internet mail order company. Okay. How many orders are filled per day? And here is the 5-number summary for the entire population. Okay. Minimum Q1, median Q3, maximum. This is population data. Okay. And they are collecting random samples of 40. Okay. And calculating the range. So the range is the max minus the min. 80 minus 20 is 60. So we know the parameter, that we know the range of the entire population. We know it's going to be 60. It is 60. But they're taking samples to try to estimate this range, okay? And they have taken 50 samples. That's why down here there are 50 dots, okay? All right, the question is this unbiased? Is this method that they've done unbiased? Okay. And well, first of all, let me back up. Like, what does a dot represent? One dot is the result. I'll write this. A single dot is the result. And what is the result? It is the range of one sample of size 40, right? Because that's the sample size. They took 40 different random days, the number of orders that were filled that day. And so they'd have 40 numbers listed down here, 40 random numbers, you know, 1, 2, 3, boop, 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 boop. They'd put them in order, and then they'd find the range. They'd take the max minus the min. And then that dot would represent that. So there's 2 dots at 53. That means there were 2 samples where they collected 40 random days, the number of orders that were filled that day. And so then they took the max minus the min. These 2 samples had a range of 53. These 4 samples had a range of 60. Okay? To be unbiased, this distribution has to be centered at the parameter. And good news, it is. I counted in 25 dots from each side because there were 50 samples. I go 25 this way and 25 this way, bringing me to these 2 dots right here in the middle, which is centered at 57. Oh, did I just say it's centered at 60? I lied. It's centered at 57. Okay? It is not centered where I want it. Okay? I want it centered at 60. Oh, that's a problem. So look at this. If the true parameter is 60, way over here, that's on the edge of the distribution. So this is biased because it is consistently underestimating the truth. There is not one dot over here at, like, 61, 62. There's question mark. There's no data over there. It never overestimated the truth. So it is clearly biased. Every single dot is underneath the parameter of 60. And the easiest way to say that is to say, look, the center is at 57. The center should be over here at 60, but it's not. All right. Thanks, folks. Happy studying.